Swayam Prabha. Digital India. Educated India.
Okay, good morning. I want to start a new topic that's pretty much the crux of this course, is on bio-based and biodegradable plastics. Okay, we'll have series of lectures in this particular topic. So now, what are these definitions? You know, what do we mean by bio-based, or what do we mean by biodegradable, right? So many times these words are interchangeably used, but there is a lot of difference between these words. So if you look at bio-based materials or bio-based polymers, whenever you say that, it basically means that as per the United States Department of Agriculture, it has defined that materials or polymers that contain at least 99% of its mass coming from an organic source. Okay, organic source meaning it could be naturally growing plants or plant produces or plant wastes, etc., etc. Anything that is coming from earth as an organic source. Okay. For example, I've given a lot of examples here. You could actually derive polymers from various food products like, you know, corn, potato, tapioca, rice, wheat, right, maize, etc. So from many of these food grains you can extract starch. Okay, or starch is one kind of polymer. Then we say that is a bio-based polymer. There are also vegetable oils like palm oil, castor oil, linseed oil, and soybean oil, rice bran oil. You know, there are so many oils from which also you can derive polymers. Okay, we can say those polymers are also bio-based. There are also polymers you can draw from animals and marine lives. For example, from the crab shell, from the bones of mammalian animals, you can also draw some polymers, which we call them as proteins. Okay, so there are classes of molecules, polysaccharides, oils and fats, and proteins. Okay, as long as you derive them from a 99% of its mass from a bio or organic source, we call them as a bio-based polymers. Right. Now there is another terminology which we say biodegradable polymers. Biodegradable polymers means that these are polymers that are converted to biomass, CO2 and water, okay, through various thermochemical processes in a specified time frame, in a specified disposal environment. Okay. If I have a polymer, regardless of its source, if it's able to convert into biomass, carbon dioxide and water in certain time, in certain conditions, we call them as biodegradable polymers. So what do I mean by environment? This environment may mean many things. It could be a composting condition as per ASTM D6400 standard. This is American Society for Testing of Materials standard, ASTM standard. Or it could be a marine situation, it may be disposed in oceanic conditions, or it could be in landfill or soil. Under these conditions, one of these conditions, whether a given polymer is able to degrade in a given time frame. When I say degrade, I mean it has to convert into carbon dioxide, water, and then biomass. So these are the kind of broad definitions, right? So you can clearly see when we say bio-based, we are associating ourselves in terms of what is the origin of the polymer. We are not talking about end of life. Whereas when we think about biodegradable polymers, we are not saying anything about the source, but I am talking about end of life characteristics. Okay, so the two terms are very different, not necessarily mean the same thing. Okay, one associates its importance to the origin, where is it coming from. Okay, and the second one is what is the nature of the biodegradability. Right. Now we have a series of bio-based polymers we can think of. The most pertinent one and it's very widely used is this sugarcane bagasse. Okay, so the picture that you see here is basically the sugarcane bagasse. If you are coming from hostel in summer, you get sugar cane juice on the roadside. Okay, you see there is a small pressing machine in which they feed the sugarcane and then you get the juice out of it. What is remaining after the juice extraction is basically a set of fiber which we call them the bagasse. Okay, so you see this kind of natural material. Now, interestingly, you can actually derive kind of polymers from these bagasse. Okay, so you can see that if you have about 1000 kilogram of sugar cane, about 280 kilograms of bagasse fiber can be extracted. So high amount of bagasse is actually there in the sugar cane. Okay, from a chemical standpoint, what this bagasse means? Okay, well, it actually means that it contains cellulose, hemicellulose, lignin, and others. These others include some volatile solvents like water, ethanol, some ash, some other inorganic matter. Okay, so basically these three are the natural polymer that we are interested, right? And as you know, the sugar is say India is probably the second highest producer of sugar. Every sugar mill is going to give you this bagasse. Traditionally, this sugar, this bagasse is actually burned for fuel. Okay, maybe mixed with coal, or it's sent to a cement mill to burn it off. Okay, as a firewood. But it also contains rich amount of cellulose, hemicellulose, and lignin, and we can use them for drawing polymers out of it. Okay, so I just want to give a little bit of a chemical details of what we mean by cellulose, hemicellulose, and lignin. If you think about cellulose, it's basically a glucose molecule. So you see this is an individual glucose molecule, right? And it is basically, so you basically link this glucose molecule into a chain. Okay, so cellulose is nothing but a linear chain of glucose molecule linked. Okay, so you can see that this entire thing is basically a polymerized glucose, which is what we call as a cellulose. Okay, so since it's a linear and same repeating unit, so it's basically a homopolymer, it is linear, so it is easy to crystallize. Okay, so that's what cellulose, pure cellulose can form a nanocrystallize. Okay, it can form into crystalline polymers. The repeating units, if you see, it has this formula C6H10O5. So that is cellulose for you. You can see that the linkage group is this oxygen here between. So suppose if you bring another sugar molecule, you will basically link them through this these bonds. Now there is another thing called hemicellulose. When I said cellulose is a linearly linked molecule of repeating units of glucose, hemicellulose on the other hand is very highly branched, and also it contains not only glucose but also contains other kinds of sugar, xylose, glucose, and galactose. It's a more of a heteropolymer. It contains many kinds of sugar molecules in its repeating units. So as you can see before, in the case of sugarcane bagasse, majority of them actually is cellulose, and I have about 25% are hemicellulose, and the hemicellulose are branched, highly branched amorphous molecules that may contain many kinds of sugar, xylose, glucose, and galactose. Remember again, sugarcane is an agricultural product. Okay, so the depending upon the nature of the environment in which sugarcane is cultivated, depending upon the amount of nutrients available, how much glucose, how much xylose, how much galactose is available, the plant will try to make use of it and change its proportion also. Okay, and the lignin is more like a binder. Okay, so you can see lignin has the most complex structure. It is basically an aromatic, it's hydrophobic, and it has all this, a lot of this COH groups, OH groups connected to this amorphous aromatic rings. Okay, so if you look at these fibers, okay, these fibers are basically consist of three major components. You got the cellulose, which are basically linear molecules of glucose repeating units. Then you have hemicellulose, which is a amorphous branched chain containing many kinds of sugar, okay, xylose, galactose, glucose. Then you have this lignin, which is an aromatic amorphous hydrophobic molecule, which kinds of binds together these materials. All right, so now if you think about this bagasse, so and then when you try to extract cellulose, hemicellulose, the most important thing is to remove the lignin. Okay, and to remove lignin, what is typically done is you put a very strong acid or strong alkali, okay, to break the chemical interaction between the cellulose and lignin, and you basically remove the lignin, and what you are left with is this fiber, okay, cellulose fiber, which is cellulose and hemicellulose. So typically if you look at this pulp, okay, the pulp is basically the lignin removed part. It looks like a pasty material, right, in water. Typically these fibers, bagasse pulp fiber would have about a diameter of roughly between 10 to 13 micrometer, and the length can be anywhere between 50 to 60 micrometer. Okay. So if you think about the aspect ratio, then we are talking about 4.5, 4 to 5 aspect ratio. The glass fiber that we use as a reinforcement in many of the polymers are typically of 100. Okay. So whenever you try to have a fiber as a reinforcing material or a strength, you need a long aspect ratio, high aspect ratio of the order of 100. But the cellulose fiber obtained from a bagasse, sugarcane bagasse, has about 5. Okay. And then if you consider the same cellulose, hemicellulose from wood, okay, the trees, they would have an aspect ratio ranging from 60 to 100. So what we are saying is, whether you take the cellulose from sugarcane or wood, chemical natures are the same, but if you look at the fiber dimensions, the cellulose that you get from wood would have longer fiber, higher aspect ratio, whereas the same fiber we obtain from sugarcane are little shorter. Okay, so that's a huge difference between the two. Even though the chemical natures are same, but the physical dimensions can be quite different. And so what do you do with this pulp? Okay, you can watch a lot of YouTube videos about making of sugarcane bagasse pulp, disposable containers. This is abundantly available in the market. You can order it on Amazon. You can go to any shop. You will see this kind of cutleries, single-use cutleries. These are all now widely available in the market. Okay, so what you do here is you start with this the pulp, bagasse pulp. You typically add some extra additives because the cellulose as such is very hydrophilic, right? So when you try to mold into some product, you're going to have leakage, you're going to have wetting issues, right? So typically some additives are added to make it waterproof, to make it antimicrobial, to make it sometimes microwavable. Okay, any functionality that you add, just like when we went to nylon plant, we saw so many chemicals are added to nylon resin to meet a particular target application. So like that, here also a lot of additives are added to make it useful for a given function. Okay, which means it should be leak proof, it should be not it should be water resistant, and it should have enough strength, etc. Right. So what happens is, once you have that pulp, you basically put it into a mold. Okay, so you see there is a mold which has maybe a cup kind of a design in 2 dimensions. You see a cross section, right? And the yellow thing that you see here, that is basically a layer of the pulp, and you suck the water out, and then you are left with the positive and negative molds containing a thin layer of pulp. Then you bring them together and then keep them pressed and keep it at certain temperature, certain pressure, leave it there for some time. Okay, so hot pressing and drying will lead to whatever shape that you want. Okay, so which shape you want, you basically build the mold. Okay, so now the mechanical property and functional property of all this will have to depend on the nature of the fiber you have drawn, what are the additives you added, and what are the thermal condition you provided to compact them. This is perhaps the most easiest thing to do. That's why a lot of people are doing it. Okay, because it doesn't require much science and optimization, right? And paper making is something all of us, our civilization knows for a very long time. Okay, this is basically a modified paper making process, right? So now this is the example I've given is only for bagasse or sugarcane. But if you look at around you, okay, from place where you're from and what's your your folks are doing, you will see that you have so many fiber source. Not only the sugarcane bagasse, you have bamboo, you have banana, broom, coir, flex, jute. You can the left hand side basically tells you how much amount of natural materials are available to us for use. All of them will differ in terms of its chemical composition. Maybe some natural fiber would be rich in cellulose over hemicellulose, or maybe some of them are actually more in hemicellulose than cellulose. Lignin will always be there to a certain extent. Okay, that's what hold the things together. Now these plants, as they grow, they consume glucose, sugar, to build its own leaves, stems and various parts, and they have a biological function to act. And depending upon the nature of the ingredient and its biochemical mechanisms, they will try to build a cellulose or a fiber material. Okay, and what we could do is, actually there is enormous potential. What they have been doing mostly are very few, but for a country like India, which is mostly agriculture based, so we have a very wide range of biomass that is available at our disposal. Okay, so I want to give you an activity for the rest of the time here, that you can take a look at this table and you can choose any particular fiber source. Okay, I was recently watching a YouTube video where they have taken pineapple crown. You see the pineapple crown, when you cut it off, you are actually not using it, but it comes along with the fruit. That the pineapple crown has a lot of cellulose. Okay, so there is a Brazilian company harvest those crowns from fruit wastes, and then they basically again to treat with the alkali and acid, remove the remove the lignin, and you're left with cellulose. Mold it into whatever form you want. Okay, as simple as that. This does not require much technology. This can actually be done in a cottage industry. Okay, at a rural level also. Okay, essentially every village that produces any of this fiber could actually have these processing done locally and meet the requirement of plastics in that region. So the activity for you is the following. You can choose one source, fiber source from this table, and do a literature search on what are the chemical thermochemical process that are there to extract the fibers out of them, and what are the materials what are the products that are made. Okay, mostly you'll see single use disposable cutleries and containers, and also critique the limitations and advantages of that particular fiber, that particular product. Okay, so over to you.